It's my pleasure to introduce Dr. Jacqueline Mesquita for the second of her lectures in the IMSA Frontiers in Mathematical Lecture Series. And today she will be talking about linearized instability for neutral functional differential equations with state-dependent delays. Thank you, Jacqueline.
Thank you very much for the introduction. So today I will talk about this more specific work. So it's a little more specialized. So I will try to give some ideas about the difficulties behind of this problem. And of course, I'd like to thank again for the invitation to be here and to be able to talk a little about this work. So this work received the support from Alexander von Humboldt Foundation and CAPES from Brazil. And the outline of this talk, I shared it in some parts. So I will start with some motivation about this problem. Then I will talk a little about these neutral functional differential equations with state-dependent delays, especially about the linearized instability principle, the main difficulties behind to get that. And then I will talk about this other class of equations that functional differential equations with state-dependent delays, but in a more general setting, considering like a discontinuous function. And then I will talk a little about some open problems. So this lecture today will be based in two papers. So this first one is, we are still in progress, together with my collaborator in Germany, Professor Bernhard Lani-Wayda from Justus-Liebig University in Giessen. And this other one, it was already published, and it was made with my former PhD student and my co-author that unfortunately he passed away, so in memory of him here. So, but we made that when he was still alive, and we made this work about this type of functional differential equations. So I'll start with some timeline about this problem. So as I mentioned yesterday, the type of problem about neutral functional differential equations with state-dependent delay started to be more attractive after Rodney Driver. He studied about the two-body problems in electrodynamics, and he realized that the best way in order to bring the model of this type of problem was using the neutral functional differential equations with state-dependent delays. So let's talk a little about this specific type of equations with state-dependent delays. So usually we have that this type of equations, not neutral in this case, but a general one, when you consider like a delay differential equations with state-dependent delays, we have this type of equation here, where we consider this tau here as a function of the state. So this x of t is the way that I defined it yesterday. So we have not a partial differential equations here, but a partial derivative, but a function that we are considering for example, here and here, and then you have that, and then we have this. So we have this way here. And we have that when we consider this type of state-dependent delays, we have many complications, because here you have some composition between this x, and again with this tau, and this tau with this x. So this brings a lot of complications in terms of regularity that we need to deal with. And then, as a consequence, we have some problems in order to ensure the uniqueness of solution. So usually in the same way that we usually had uniqueness, existence and uniqueness solution, for this case specifically when you have like state-dependent delays, it's not so easy to ensure that you have a unique solution. So here is one example that it's bringing in a chapter of book from Hartung, Giessen, and Walter and Wu, that they show that, for example, if you consider this very simple equation here, So we have this type of equations with these initial values. We have that we cannot ensure, in that simple case, uniqueness of solution. So we can have that this and this is a solution of this problem. But if you see, this seems to be a very simple problem that if you do not have here like state-dependent delays, you can have a unique solution. So here we have we can show that it's much more complicated to have to ensure the uniqueness of the solution when we have state-dependent delays. So here also, if you see about this type of state-dependent delays, it's also possible to rewrite in that form here. However, in order to rewrite in that form, we need to define this special F0 in such a way that we have this composition here, where we have this one is the evaluation max, which means that you have this pair here, and it takes this P applied to S. So this is the evaluation map we have. And then if you define your F0 in such a way, we have a relation between the other equation and this equation here. So, but if you see, we need like to ensure certain properties concerning all these functions that we have this composition. And sometimes we do not have some regularity for this evaluation map. So that's the problem, because since you have that your evaluation map is in general not continuously differentiable, and you do not have including that this evaluation map has Lipschitz continuous property, you cannot translate the results from this equation to this other equation here. So it's not possible to transfer all the results that we have from this type of equation to the other one. Because it would be very nice if you could do that, because we know that from the books from Jackie Hale and Lurnell and the others, that there is a lot of theory behind that. So if we could have some translation, it would be very nice. However, when we do that translation, we lose regularity. And because of that, we cannot translate the results. And that's why it's so hard to do with that. So now I will talk about our specific work, and in this first part, it will be about this paper here about the linearized instability principle for neutral functional differential equations. And I will start talking why we were interested about this type of problem. So this problem is about exchange money, the currency exchange, and it was proposed for the first time in 2004 by these three guys here, the Brunovsky, Erdely, and Walter. So they brought this model here in order to understand about the fluctuation of the market and the exchange money. And they proved some properties concerning the solution. However, they couldn't prove many properties, but they made some conjecture about what would happen with the solution depending on the value that you put for A. Then later we have that Walter, he proved many properties concerning periodicity and bifurcation for this type of problem here. And later we have that these three authors, Garab, Kovacs, and Christine, they proved some asymptotic properties that were conjectured in the first paper here. So they proved many properties concerning the asymptotic behavior of the solution and what's happening when you have this A varying somehow. Then we have that Stump was one of the first to try to improve that model, considering not only constant delays as appears here, but state-dependent delays. Exactly because of these fluctuations, you have that the time is not constant, but you have that some delay that depends on the state. So he brought with that, it was his PhD thesis, and he proved several properties concerning the solution of this problem. So then in 2013, Hans-Otto Walter, he improved even more the model, and he realized that it needed to put some derivative here in order to have a more realistic model for this case. And then now what we have here, we have a neutral equation for this type. So now because we have the derivative in the part that you have the delay. So now we have a state-dependent delay, and we have here the derivative in the part of the delay. So now we have a lot of complications to deal with this problem. So then Hans-Otto proved several properties concerning this problem. He proved existence and uniqueness of solution, differentiability, and also linearized instability principle for this type of equation. However, the linearized instability principle was an open question, exactly because it's not easy to have this type of problem to solve, because usually when we linearize this type of equation and we see about the spectrum, we can see that we can have infinite eigenvalues, and then we can have some problem to have some estimates. So that's why it was so difficult to have this type of solution, let's say, for the linearized instability principle. And then we decided to investigate about this problem. So here is the problem, as you saw before. And then the first thing that Hans-Otto made in order to prove his results was to transform that problem in this abstract form here. So, and then we made the same, we follow the same steps in order to work with this more general type of equation. And it was very nice because in our case, we could find out another model that also can be used in that way. That's about some mechanical engineer, so some pendulum that we could work on that direction, and it fits the same hypothesis as here. And so we had two models in order to motivate our investigations for that problem. But then the first idea is to translate this type of problem and these more general ones and see if it satisfies certain conditions of regularity in order to prove our results. So here we have these conditions that I will explain. And here, just remembering that this means exactly the one that is here. Other thing that's important is that Hans-Otto worked with this everything in R, but we passed everything to Rn. Of course, it was not a big deal. It was very easy to pass it. But only to mention that we made that everything to Rn also, because for our other model, it would be very important to be in Rn. So that's why, but of course, the accounts were very similar for that case. So here, in order to rewrite this equation in the abstract form, so what we need to do? So we need to use those evaluation maps that we saw before. So here we have the evaluation map that we had. So that takes here and applying here. So we have that. And here we have the restriction of the evaluation map when you consider in your second variable C1 instead of C. And then with that, and with these two evaluation maps, we can rewrite in the following way. So here we can rewrite our G in the compositions, where we have here is the projection concerning the second factor, and here is the projection concerning the first factor. And then using those evaluation maps here, and here's the restriction of the evaluation map, we can rewrite our equation of the model in that abstract form. So that's why we would like to have that. And then let's see about the conditions that we have. We know that some of these conditions can be too technical, and I will try to pass lots of details because it's too technical, but only to mention that our two models fit on those conditions. So that's okay to us in our opinion, because since we have these two models to motivate, that's nice. Of course, we could like prove some conditions, and we are including trying to do that, and that's why we didn't submit the paper yet. But it's something that we are still working on that. So here we have the first one is about continuity of the function. That's okay, that's nice. Here is something that we asked that's about that in the delay, the neutral part never vanishes. What that means in some way, if you try to understand what that means here, so what we have is that these two are equal here, but then this implies that we have these two are equal. That means that does not matter what's happening from minus delta until 0. And if they are equal in that interval, so you can ensure that they are equal when you apply G. So what we have here is something like that. So -8 minus delta. So here you have like a phi1 equal phi2. So it doesn't matter if they are different here. What will happen is that G, when you evaluate it on that, will be equal G when you evaluate it on that. So that's very important to us because you can ensure that the delay here is never 0. So it's good for somehow, but of course, depending on the model, it could be not so nice because if we had, for example, the problem in electrodynamics that you have the chalk, so in that case, we need that it would be 0. But in our specific case, there is no problem because we do not have this type of model. So here we have another other condition that's about local estimates of G. And this is the type that we expect. That's about like Lipschitz condition for our function G. That's something that we are expected in order to ensure about the regularity. And this one is very important property, this G3, because it will help us in order to construct our manifold, in order to have this linearized instability principle. So what that means, so we have here this linear extension of the derivative dg. So here what we have is that you have this G1, that's the restriction of G to this open subset that you have here C1 times C1. And then you have that every derivative that is defined here in C1 times C1 has a linear extension, which means that you can have that this extension here defined as C times C. And using that, we can define our manifold, which will be very important to us in order to prove our linearized instability principle. So this condition was introduced before and used by many people, and it's called like almost differentiability. And it was used by John Aleparre, also Nussbaum, and others. So we have that this condition is like a type of usual in the literature when you deal with that in order to define this type of manifold. So here using this property, so what we have is that, so we have that this set, if you define all the functions here that are in U1 intersection of C2, such that we have our equation here, we have that if this set is not empty, we can have that this one here is a manifold. So we can have this structure of the manifold for this, using, of course, this norm here. And it's very nice to think about that, because here we will use that, but of course we will need to define another manifold after. But here, one thing that happens in that case is that it's nice because we have this structure of the manifold, but we do not have the invariance. So, and we need now to define another subset that we can ensure the invariance of the set. But we will see this later. So here we have another condition. This condition before, we think that is too strong, and now we are trying to avoid that. But we are using this condition for a while, but we think we know how to suppress this type of condition, and we're thinking maybe to not to use that. So here we have this distinct that's about upper semi continuity, and then this other one that's about these estimates. So then what we have is that our G defined in that way, it will satisfy all those conditions. So all those conditions will be satisfied in that case. So that's nice to us because we have all those conditions in order to prove our results. So now we have this equation here. And then the definition of a solution for us will be like a continuous differentiable function will be a solution of this type of problem if of course it satisfies the equation. And if we have this pair here belongs to this W, that's an open subset of C times C1. And then if we have that, we say that this is our solution of the problem. So now, as I mentioned before, we have the manifold that it was nice. However, our manifold was not invariant. So that's why now we need to define this following closed subset, this xg2 star, that is defined this way here. So you take all the elements, the manifold, such that satisfies this condition here. And then what we have is that this one now is invariant. So Hans Otto Walter, he proved that. So if you start here, you continue on that in time. So now, as I mentioned, what we would like to show is about the linearized instability principle for this type of equations. So you start proving that zero is unstable, and for that, we will use the invariance of the form. So it will be our strategy to prove that. So first we prove that for the abstract conditions, but then we come back to our specific conditions to see what the interpretation behind. So here we prove it in a more general setting of the hypothesis. So here first, what we have for hypothesis is that we can split the space in unstable parts and stable parts. And what we have is that this is like the estimates for the unstable part, and here is the estimates for the stable part. And it will be very important to us, these estimates, in order to prove our results. We were a little doubt in the beginning if we could have this type of hypothesis in our case, because as I mentioned before, when you see about the neutral equation and when you linearize that, what happens with the neutral equation is that when you look for the spectrum, you can have infinite eigenvalues. And because of that, sometimes it's very difficult to have some estimates from below for your same group. However, here we saw that it's also possible in our case. We could see many possibilities of functions and using our equation that we could construct some neutral that we could have these types of estimates. But we can have some situation that is very hard to have these lower estimates for the same. So here we have the other properties that's concerning the semi-flow, and this we win from papers from Hans Otto Walter because he proved everything about the existence of the semi-flow, the differentiability of the semi-flow, and in our case, in our specific equation, we have those properties. So here it's only asking about these properties concerning the semi-flow. So here what we have this A3 is the difference between the nonlinear and the linear. So here, this R is the difference between the nonlinear and the linear part. And what we want to have with this condition is that when you do that difference here, and when you apply the T1 map, what we have is that this is small. So you have that they are like close. You have the nonlinear is close from the linearization that you have. So that's what's behind of this condition, and we could show in our specific case that it's also okay because we use the variation constant formulas for our solution, and then we use the solution of the linearized problem and make the difference between them, and using the hypothesis that we have, we could do some estimates in order to prove that in fact we could have this inequality here. So, of course, here, if you see, we have here the estimates appear all the time in this K. And in order to avoid to use all the time this constant, we will use an equivalent norm in order to consider this K equal 1. So here, only in order to not use all the time this K with us, to not have a very heavy notation, we will use here this equivalent norm that we will denote it by this, and we will consider that our K is equal 1. So here we have the estimates considering that K is equal 1. And then here what we will have is that if you take an element of your space, so you will have that since your space can be have this format of the direct sum, we have that the elements will be like that, and here the norm will be the maximum of the unstable part and the stable part. So here now we define the cone. So we take our C here, and we define this cone as all the elements here in the space. This is in the stable part, and this non-stable part, and we have this inequality here. So we have now this invariance of cone and expansion, and what that means. So here what we have is the following. So we have the C here, and we take T1 in a way that we have the assumption A3 is satisfied, and also we take this Q equal this here, and then we have that Q is bigger than 1. And what we have is that if you start in the cone here, you start in the cone, you start in X in the ball, what's happening is that when you apply the T1 map, you are still in the cone. So here you have the invariance of the cone, because you are in the cone, you start in the cone, and then you apply the T1 map, and you are still in the cone. And then what you have more than that is about the expansion of the unstable part here. So what's happening here is that this is the new unstable part, and you have that bigger or equal these estimates here, but this Q is bigger than 1. So you have an expansion of the unstable part. So let's give some idea of the proof only for you understand a little on the techniques behind. So here we have, we would say this epsilon as this minimum here between these two quantities. And we will take our delta in a way that we have the assumption A3 is satisfied. And then what we have is the following. So here we apply the projection of the nonlinear part in the T1 map. And then what we have, if you remember, here we have that this is the difference of the nonlinear part and the linear part. And then, so using that definition, what we have is that this one here can be written in that way here. Then passing this projection, so we have that. And now we using the estimates that we have in assumption A1 about the same group here applied in the unstable part. Of course, using the inequality to the other side, and using the last hypothesis about that when you apply the T1 map here, we have that this one is smaller or equal epsilon times the modulus of X. So what exactly we have here? So we have this inequality here. And now again, using the property concerning this projection here, we have this other inequality. So we will use this inequality later. So we will leave it here only to remember, but we will need that later. So now we do the same, but for the stable part. So now we apply the projection in our T1 map for the stable part. And again, using the definition here that we know that this one here is the difference between the nonlinear and the linear part. We have this equality here. And now passing the projection, we have that. And then using triangular inequality and also the estimates for the stable part, we have this inequality here. And then now using the property concerning the projection, we have this other inequality. So now we have these two inequalities that will be very important to us. So now what we want again, we have this here. If you remember, that's our function that has the nonlinear part, and here is in the T1 map. And if you remember the definition of our norm, we have that this one is the maximum of the projection for the stable part, and here the unstable part. But here we have that this one here is smaller or equal that, because we saw that before. So here we have this maximum. Is this more or equal this other maximum here? So now we have these two possibilities. Okay, so we have that this is more or equal this maximum, and this maximum could be this or could be that. So we will now see all the possibilities. So suppose now that this maximum is this one here. So in that case, what we have is that this one is more or equal that, because this is more than maximum of here. So we have this inequality here, and considering that our C is more or equal 1, we have this other inequality here. And then what we see here is exactly that the definition of the cone. So here we have the T1 map belongs to the cone. So here we have the invariance of the cone for that case. So now we have this other one. We will now consider the possibility that the maximum is the other part. So using that, we have this inequality here that follows because that. Now we only sum and subtracting this term here. So we have this equality here. And now using the definition of epsilon, we have this other inequality. And now using the estimates that we make in the beginning, we have this other inequality here. So we have, again, this inequality that using the definition of cone, we have again that T1 map belongs to the cone. So here we prove it for all the possibilities, the invariance of the cone. So now we need to show the expansion. But for the expansion is very easy, it's not difficult. So here we use the estimate that we have for the unstable part that's given by this. And here we use the property that X belongs to the cone. So we have this inequality here. And then now using the definition of epsilon, we have this other inequality. Making the account here, we have this is given by that, but this is exactly the definition of K. So Q. So now we have this inequality, which means that we have the expansion. So we prove it the invariance of the cone and also the expansion. So we prove it for the abstract way, as I mentioned. However, we can translate all these results for our specific case. So here we have the abstract framework. So here we have this E, we can translate as our C0. This E2, we can translate our C2. This X, we can translate as this invariant set, that XG2 star, and this is the linear part. So now, in our specific case, what we have, if you remember, we have that manifold that we constructed, the XG2, and then we have the other one that the closed subset that invariant, that XG2 star, this one here. But then what's happening is that XG2 star, it's invariant. However, we do not have the structure of a manifold. We have, but we do not, we don't know if it's a manifold. So we need now to define another set. So in order to ensure that's a manifold. And in order to do that, we need an additional hypothesis for our specific case. So here we have this A that is our like other hypothesis that's very close to the one that we talked before about the linear extension of the first derivative. But here we will use the second derivative. And also we will ask about the linear extension. So here we have our G1, and then we have that this one here, the second derivative, has a continuous extension to C times C. So using that, we now can define a manifold. So we can have that our M3, that's the intersection of XG2 star with a C3, now it is a manifold. And using that, now we can prove our result. So we need this additional hypothesis here. So what's the main idea behind the proof? So here we have our manifold. And what's happening is that we start in the manifold, we start in the cone, and then in the ball, and then we apply the T1 map. and see what's happening with our solution. When you apply the T1 map, we can see if our solution escaped from the ball, we proved instability. However, our solution maybe cannot escape from the ball. But what will happen if it's not escape from the ball? We know that our solution continues in the cone because we proved the invariance of the cone. And we know that our solution may escape it from the manifold, but we know from the definition that our manifold, the definition of the manifold is M3, is X G2 star intersection C3. So it may escape from the manifold. However, it is in that set, and this set is invariant. So it will continue in that set. So you have that your solution is in the cone and is in that set. So then you can apply another time to see what's happening with the solution. And if it does not escape from the ball, you can continue with that because you have that your solution. You will continue here because this is invariant, and it will continue in the cone. And if it does not escape from the ball, you have some contradiction because you have the expansion of the unstable part. So in some moment, your solution needs to escape from the ball. Because of that, you cannot arrive in a sum of contradiction because you are the expansion of the unstable part. So with that, we have this linearized instability principle. So here is the linearized instability principle that we proved. So as we mentioned, we have that there are some time that our solution will escape from the ball. And we have that because of the expansion of the unstable part in our cone. So it was the first part that I would like to mention that we proved this linearized instability principle. Now we are trying to improve this result. We think that it's nice, but we are trying to suppress that condition that we think it's too strong. In our case, of course, it will work for our models. So both models that we had, the one about the current exchange and the other about mechanical engineer, both models fits in that in those conditions. But we are trying to avoid that because maybe in the future we can find another interesting model that cannot fit. So that way it would be nice to avoid that condition. Other things that we are also trying to improve is about the linearized instability principle, because it was proven in a very simple form. And we are trying to see if it's possible to improve it for like exponential stability, but in a better way. So we are trying to see if it's also possible or not. But of course, until now, what we have is only this one here, and we hope that we can finish this very soon. So now, I will very briefly talk about this one, only give the idea behind of the paper, but I will not enter deeper because of time, but only to give some ideas about this type of problem, about functional differential equations with state-dependent delay. So here in that work, we worked with this type of equations here. And again, here what we have is a type of state-dependent delay, but it's much more. It's like a state-dependent and time-dependent delays, both, because here now your delay depends on time and depends on the state. So now we have both. It's a little more complicated. And here, what we made that it was nice, it's because usually when you see in the literature about this type of problem, always they consider this x as a continuous function in order to have this type of regularity. But in our case, we would like to see what's happening if our x is a regulated function. And here we have some trouble because what happens is that if you have here, for example, x, and then if you apply in, you put this type of if you write this thing here, what happens is that here you have this composition. So you have a composition of X with something with X. And here we can have some problems if you are working with a regulated function. Regulated functions, only to recall, is that the one that the lateral limits exist. So it does not need to be continuous. The only property is that the lateral limits exist. So if you compose regulated functions with regulated functions, we do not have that it is a regulated function. So here we can have problem because of these compositions. So we try to see in that paper which conditions we could have for this whole here in order to ensure that this type of composition would make sense. So you would have something interesting. And it was very nice because we can also apply that for many different types of models. And it was very interesting about that. Also, here we needed to define a phase space because we could have here infinite delay. So we could work on that situation. And we use here the phase space, we were inspired from the phase space of Arino at all. But here we worked with a regulated function. So we needed to change a little the properties. So we could apply also our results to this type of equation here, and it was very nice because we could also have some real world models in our problem. So I'm not enter deeper on that. It was also very technical, but it was very nice because we also could apply our results in these types of models. So now I will talk very quickly about some open and developing problems in that area. What are we trying to think about? So now, first about this first problem, the linearized instability principle. This type of equation that you saw before, we have many open questions for that, like periodicity, bifurcation. We don't know what's happening in this type of equation. So we'd like now to search more to try to understand what's happening with this type of equation, with this qualitative properties. So all these are completely open in that direction. So concerning the second problem that you saw before, I also worked with my former PhD student and also Professor Bernhard with other types of problems, considering this situation here of state-dependent delays. And when you have that your X can be discontinuous. So we could have some relation between this type of problems and more general equations like generalized ODEs, thinking about other types of integration, for example, Kurzweil-Hansdorff integration in order to have a highly oscillating function. So we also could thought about this type of problems because we have some pendulum models that we have this highly oscillating function that it's very nice to use this more general integration in order to work with that. So we work in several problems in that direction, since we could have a more general types of solutions for those types of problems. So we work on that direction. And also now we are trying to work more in mixing, having a type of a Volterra integral equation. And because I'm thinking maybe of the possibility to have here like state-dependent delays, we don't know, and using like Still's integral here, so it could be something like that. Or also you could have a distributed delay if you want, also considering the integral. But the main things of this type of equation here is that you have this type of kernel. And using this kernel, depending how you define it, you can have the fractional inside. So fractional differential equation, and you can have many models that can be used with fractional. Also here, this G, depending how you define it, you can have like impulsive behavior. So also we can put like impulsive equations inside of that. And also you can have like difference equations, dynamic equations, different time scales. So we can have many situations for that. So we think that can have a lot of interesting applications behind of this type of more general equations. So I had a PhD student that defended a very few months before I come. And she worked a lot in this type of equation here. She also worked with some colleagues in Germany. She made like a sandwich PhD and worked with this type of problem and the applications of these for many different models. So it was also very interesting to work with that. And yeah, that's it. I think there are several interesting problems to think in that direction. So that's it. Thank you very much.